integration area under a curve, type 6, curve and curve. So this is very similar to finding the area enclosed by a line and a curve. But this time, rather than having a line and a curve, we have two curves. So it's the same process is applied. We look at which function is higher above the other. In other words, which one is going to have the greater area between the x-axis, the limits, and the curve. So we can see that f of x is above g of x. So if I was looking at the area under f of x, between the limits of b and a, we would end up with all of this shaded area here, where that's f of x. And then obviously if we were looking at g of x, if I separate that out, well, g of x is down here. And again, if I'm looking between a and b, then the area enclosed by g of x, the x-axis and the limits a and b, is all of this purple bit. So basically, if I was to sketch f of x on top of g of x, then we would see that if we subtract the green from the purple, we would be left with the area that we're looking for, which is this blue shaded bit here. Okay. So in other words, if I get the difference between the two, we get the area enclosed. So we say the area enclosed by the two curves is equal to the area under curve minus the area under the curve. And obviously you're taking the bigger area and the smaller area. Okay, so a little sketch is always help you figure out which one you're taking away from which. Okay, so let's have a look then at an example. So we are asked to find the area enclosed by g of x, which is equal to 21 over 16 x squared, and f of x, which is equal to x squared plus 5. So we're getting the area enclosed in the shaded area here, which is green. Now, we're not told what the limits are, so we have to work out what the limits are first of all. Now, obviously, we can kind of see what it's going to be from my graph because I've put in an axis on it. But in an exam situation, they generally won't have your x and y axis labelled here. It's just because I've used GeoGebra to draw this graph. So to find the points of intersection, the first thing we're going to do is take our two graphs. So basically, we have y equals 21 over 16x squared, because y is the same as saying g of x. And we also have f of x, in other words, y is equal to x squared plus 5. So because they're both equal to y, in other words, if we input for x, our outputs are always our y values, our y coordinates, then I can equate 1 and 2 to find the points of intersection. And then that will give me my limits. I'm not asked to find the coordinates of the points of intersection here, so therefore I do not need to find y. However, if I was asked for the coordinates first, I would have to find both x and y. Okay, so I'm going to multiply across by 16 here just to get rid of this fraction, make it look less messy. So 16 times x squared, and 16 times 5 is 80. And then if I bring everything to one side, we have 21 minus 16, which is 5x squared, and that's equal to 80. And then x squared is equal to 16. And as we can see from my sketch there on my graph, if I get the square root of 16, I get plus or minus 4. So therefore my limits, my upper limit is 4, and my lower limit is minus 4. Okay, so now what we want to do is find the area under our curves and subtract them. So we can see that f of x, in other words our x squared plus 5, is above g of x. So it's going to be the area of f of x minus the area of g of x. So the area enclosed by the curves will equal the area from f of x minus the area of g of x. And of course we find our area by integrating our two functions. So again, you can work them out separately. I'm going to call them area 1 and area 2, or you could do it all in one go. So area 1 is basically equal to the integrand, I should say, of x squared plus 5 dx. My upper limit is 4 and my lower limit is minus 4. So in other words, I'm getting this part of the curve. So that would be all of that. So if I integrate x squared with respect to x, I add 1 to the power and divide by the new power. Integrate 5 and I get 5x. Sub in my 4 and my minus 4. And then again, be careful when you're subbing in minus 4. And watch your signs. Okay, so if I put that all into my calculator and simplify, I end up with 41 and a third minus 41 and a third, which gives me 248 over 3, or 82 and 2/3. And again, that's square units. And then I'm going to do the same for area 2. So area 2 is equal to g of x between the limits of 4 and minus 4, where we said g of x was 21 over 16 x squared dx. So if I integrate x squared with respect to x, I add 1 to the power, which makes it x cubed, and I divide by that new power, which is 3. And then I put in my limits of 4 and minus 4. So let me just divide 21 over 16 by 3 there. And that's the same as saying 21 over 48 x cubed between the limits of 4 and minus 4. So now I'll sub in my 4. So that's going to be 4 cubed minus 21 over 48 times minus 4 cubed. So again, very carefully putting all of that into your calculator. And that will give us, so we get 28 minus 28, which is 56 square units. Okay, so we now have area 1 and area 2. So to get the area shaded or area enclosed, it's going to be area 1 minus area 2 so that is 248 over 3 minus 56, and therefore the area is 80 over 3 square units. Okay, so nothing new. Again, just really being able to break down your image into the upper and the lower, the bigger area minus the smaller area. So page 412, you're going to do 2 questions. So you're going to do question 5 and question 6. So type 7, we're looking at the trapezoidal rule again. So we're revisiting this from when we were doing area and volume. And at the start, when we were looking at getting the area under a curve, we were saying that we could see that it had been derived from our trapezoidal rule, where we're getting an infinite number of trapezoidals under the curve itself. So the more of these there are, the more accurate the approximation is. Whereas with integration, with a definite integral, you're getting the exact area. So often in the Leaving Cert, we can be asked to compare the two and get the percentage error of using the trapezoidal rule rather than integrating. So again, just a reminder with the trapezoidal rule, its area is going to be h over 2, where h is the width of each of the intervals, and then it's times the first height plus the last height, plus twice the sum of all the other heights. And of course, this can be found on page 12 in your maths tables, making sure you're using the trapezoidal rule and not Simpson's rule. So Simpson's rule is gone from the course. Okay, so let's have a look at an example where we would be given this kind of situation. So this was an interesting mock question one year where we had the St. Louis Gateway Arch. It's often mistakenly described as an inverted catenary arch. So that's basically a curved form when you allow a chain or a cable to hang from its two ends under its own weight. So we're given an equation that is represented by this arch, and then we're given it between the domain of minus 96 for x all the way up to 96 for x. And we're given that x and y are measured in meters. So we have to fill in the table by rounding off y to the nearest meter. So that's really important when we're subbing in here. So basically what that means is that we're going to sub x equals minus 96 into our function y. So if I sub that into y there, we have y is equal to 231 minus 19.57 times e to the power of 1 over 39 times minus 96 plus e to the power of 1 over 39, minus 1 over 39 times minus 96. And again, we have to put that into our calculator. So again, be very careful when you're subbing in e to the power of on your calculator. And to the nearest meter, we end up with 0. So we sub in here and we get 0 for x equals minus 96. So we're then going to do the same for minus 64. So when x is equal to minus 64, let's sub in. So we have y is equal to 231 minus 19.57 times e to the power of 1 over 39 times minus 64 plus e to the power of minus 1 over 39 times minus 64. And again, subbing into your calculator, nearest meter, and we get 126 meters. Okay, so you're going to keep going. So when we keep subbing in, we end up with x equals minus 32, then y is equal to 178, and when x is equal to 0, we get y equals 192. So again, if we keep going and I sub in here into the table, we end up finding that we get to our highest point, and then obviously we get equal on the way back down again. So the same values on the way back down. So the next thing we were asked to do then was, based on those points that we have just found, our x and our y values, we're going to plot our function, and then we're going to use the graph to find the maximum height and also its height when x is equal to 50. So maximum height would be the highest point on the graph, and then the height, in other words the y value, when x is equal to 50. And then we're going to find the true value of its maximum height. We're told is 630 feet. And we have to find the percentage error to three significant figures, given that 1 foot is equal to 0.3048. And then once we've done that, we're going to use the trapezoidal rule to find the area under the Great Gateway, and that's to the nearest square metre. So let's sketch this graph first of all. So if we sketch our points, we end up with this shape of the graph, which is to match the archway. So to find the maximum height, and that's the highest point plotted. So our highest point plotted we saw was when x was equal to 0, y was equal to 192. So we say max height is equal to 192 meters. And then when x is 50, so we go across to 50, and we go up, and we go across, and therefore we get, when x is 50, y is equal to approximately 155 meters. So then we're asked for the true value. So our true value is where we have 630 feet. And I convert that into meters. Well, 630 times 0.3048. I get 192.5 0.024 meters. So of course then the percentage error is the difference between the true value and the calculated value. So our true value is 192.024 minus 192, and that's divided by the true value, multiplied by 100 over 1. So then that gives us a percentage error of 0.0125%, and that's corrected 3 significant figures. Okay, so we're now going to use the trapezoidal rule, and we have to get the answer correct to the nearest square metre. So we're going to have to divide this then into our equal intervals. Let me just remove that last bit there. And our equal intervals were already done for us because that's the values that we calculated here. So if we look at the difference there, we're going up in 32, 32, 32, 32, 32. So that basically means then that H is going to be equal to 32 meters. Our first height is 0. So the first is equal to 0, and the last is also equal to 0. So if I sub in then for my area is approximately equal to H over 2, my first height plus my last height, plus twice the sum of the rest. And that's the sum of the rest of the heights. So therefore I can say the area is approximately equal to 32 divided by 2. First and last is 0 plus 0, twice the sum of the rest of the heights. So these heights here are my y-coordinates. If I go back, my y-coordinates were 126, 178, 192, 178, and 126. So subbing that in here, we have 2 times 126, 178, 192, 178, and 126. So the area under the curve is approximately equal to the nearest square metre, 25,600 metres squared. Okay, so the last thing it wants us to do then is to find the exact area. So if I want to find the exact area, I must integrate my function, which was 231. So 231 minus, and I'm going to multiply out the brackets here, 19.57 e to the power of 1 over 39x minus 19.57 e to the power of minus 1 over 39x dx, and that's within the limits of 96 and minus 96. Okay, so let's integrate. So if I integrate 231 with respect to x, I get 231x. If I integrate an exponential function, I get itself, but I have to divide by the derivative of the function within the function. In other words, if I differentiate 130 or 1 over 39x, I get 1 over 39. So I must divide by 1 over 39. And then it's minus 19.57 e to the power of minus 1 over 39x. And again, I must divide by the minus 1 over 39. And then I'm going to sub in my limits of 96 and minus 96. So let me just simplify this first a bit before I sub in my limits. Okay, so if we're dividing by 1 over 39, we end up with 763.23. So now subbing in for 96. And then subtracting when we sub in for minus 96. And then slipping into your calculator, and be very careful. And we end up with 26,587.772 meters squared. So you can often be asked to compare the two. So you can see you get 25,600, so a bit of an underestimate there with the trapezoidal rule. And the exact area is 26,587. So we'd have approximately 3.72% of an error there with the difference. Okay, so what I'm going to get you to do is just simply one question, very nice question, which is page 414, and you're going to do question 15. And then that finishes up with our area under the curve. So we only have one type left to go in integration before we're finished.